too. I do the same thing.
Yeah. Like just to double check it's 4.
I do
know
this in my
sometimes
mind.
6 simple numbers. I do. I'm like I don't have that much.
So, today we're going to be doing 2.2c, which is limits involving infinity, and now we're going to be talking about vertical asymptotes. So, the last few days we've been talking about horizontal and oblique. Now we're going into vertical. We'll do vertical tomorrow as well. So the important thing you need to know about vertical asymptotes is that they cannot be crossed, unlike horizontal and oblique. The only quote-unquote exception to that is when we have a piecewise function, where part of the function's over here, one part is over here. So technically, like the left side of the graph would quote-unquote cross the other part's vertical asymptote sometimes, but it's not actually crossing. It's just because of the way that the graph looks. So we are going to look at an example like that, but just keep in mind we can't cross vertical asymptotes. So the other important thing you need to know about vertical asymptotes is that sometimes, basically to find a vertical asymptote, you're looking to set your denominator equal to 0. But before you do that, you have to make sure nothing is going to cancel out, because when it cancels out, it's not a vertical asymptote, it's actually a hole in the graph. So we have to be able to differentiate between the two things happening, because they are two different things. Okay. So we're going to be looking at limits today where we approach a finite value, but the limit itself will be going to one of the infinities. Hi. All right. You need one of each of these right here. So for the very first one we're going to look at, today I'm going to provide you the graphs. Tomorrow we'll talk about when you are not provided a graph. So for today, you will have the graphs, or on homework you can use Desmos, but for the next day we're going to do them without using the graph. So anyways, first thing you always want to do is you want to look at the rational function that you're given, and you want to make sure that it's fully factored. So what do you think? Is this fully factored?
Yeah.
Yeah, there's nothing that we could factor here, right? So once it's fully factored and nothing can be canceled out of the numerator or denominator, you're just going to set that denominator equal to 0. And then you're just going to solve for x. And that right there will determine what your vertical asymptote is. Now, we also have some skills that we've learned about in the last few days. This is bottom heavy, so we know that it also has a horizontal asymptote at y equals 0. So you can all kind of see where that is. That's the x-axis. So now we're going to be looking at limits as we approach the vertical asymptote. Left, right, and then total limit, right? So as we approach the vertical asymptote on the left, what is the function doing? Going down to negative infinity. As we approach on the right, we're going up to
Positive infinity.
Good. So does the limit as we approach the vertical asymptote exist? No, because they do not match. Okay. Now we're going to look at example 1b. So first thing we want to check is, can it be factored? What do you guys think?
Well, I mean,
you can write it as
x times x.
Yeah. All you can really do is write x times x. That's not really necessary. Nothing's going to cancel out of the numerator denominator. So for that reason, I can just set x squared equal to 0. I take the square root of both sides. That gives me x equals technically plus or minus 0, but with 0, 0 is nor negative nor positive, so not necessary. So we have a vertical asymptote at x equals 0, which is the y-axis, and then because it's bottom heavy, we also have a horizontal asymptote at the x-axis, y equals 0. So now we're going to look at as we approach the vertical asymptote. So as we approach on the left, what is the function doing? Good. As we approach on the right, what's the function doing? Good. Now, instinctively, would you say that the limit exists based on this? So we're going to say yes, but I do want to mention something about this. So you're getting to a point in math where things are actually disputed amongst math professors and professionals in the field. So I do want to just give you a little disclaimer here. We are going to say that it exists for the sake of this course. However, here's the counter argument of why some say it doesn't exist. Infinity is not a number, it's a concept. And we know that the definition of a limit is that the left and right limit exist and equal each other. Two infinities to positive infinity don't necessarily equal each other. One infinity can be larger than another. So for that reason, it doesn't necessarily quote unquote exist, because technically speaking, if these keep going up forever and ever, they're still never going to cross that vertical asymptote. They're never going to actually go to the exact same value. So for that reason, technically, some would say it doesn't exist. So I just want you to be aware of that being disputed. But in this class, if the two limits match, we're going to say that the limit does exist and it's positive infinity. It serves us best in this particular course to say so. So does anyone have any questions about that? All right. So the next one we're going to look at is going to be this picture here. We're going to look at the picture and determine all the separate limits. So first thing I want to mention is if you want to, you could rewrite this as like x plus 1 times x plus 1. You know what I mean? You could write that binomial out twice. The numerator will give you the x-intercepts. So do you see how we have an x-intercept at -1 and at 3 due to the factors of the numerator? Does anyone remember why does the 0 at -1 not go through the x-axis? Does anyone remember the rules about multiplicity from algebra 2? Do you remember bounce, if it bounces or it goes through? Because this 0 occurs on an even amount of times, that means it bounces at that x-axis. So if you remember that, that's why. And then as you can see, at 3 it goes through because, of course, it's only occurring once. So that's just something to think about from past math classes. So for the very first one, we're going to look at the limit as we approach the first vertical asymptote on the left. And as we approach -3 on the left, what is the function doing? Good. And on the right, it's also approaching? Positive infinity, right? They're both approaching positive infinity. So do these two limits match? So therefore, we're going to say the limit exists. Now we're going to look at the limit at +3. So I'll zoom in a little bit. At +3, the function is actually defined, right? You see that? And does the limit exist? Is it approaching the same thing on both sides here?
Yeah.
What y value is it approaching at 3?
0.
0. So that's kind of like the original limits that we learned about in this class, right? So this is 0. And then at 1, does the limit exist?
Yeah.
Yes. It exists at,
Maybe 1, maybe 0.5.
yeah, about 1/2 or 0.5. And then at 0, it actually gives us that exact value, right? So at 0, they give you the exact value of 1/6. So that one does, in fact, exist. All right. So now we're going to be looking at the other vertical asymptote, the 2. So on the left side of the 2, what is the function doing?
It's going up.
Yep, to positive infinity. And on the right side of the vertical asymptote, it's approaching?
0.5.
No, it's going down to -infinity. So does the limit exist at?
2.
No, does not exist because they do not approach the same value. Okay. So you do have some piecewise graphs on your homework. I'll pass it out. Just be careful because remember, piecewise graphs are only defined under a certain boundary. So make sure that you don't confuse those two things. All right, I'm going to hand out your homework now.